In this video, we'll be exploring the EUV comparison tool on Predictive Science's new MHDweb 2.0. This tutorial is part 10 of a 12-part series that is designed to guide users through this website's data visualization tools. If you've not done so already, I recommend that you review part 1 of this series. It covers in greater detail the website's architecture, general visualization workflow, and the mass run database. So with that being said, to get started with EUV comparisons, navigate to the MHDweb landing page, that is predsci.com/MHDweb2, and click on the EUV Imagers button here. As with the EUV and X-ray tool, I'm going to select Carrington rotation 2290 and Thermo 2 for that. As a first-time user of this tool, I recommend clicking the Reset Values to get a properly scaled and normalized plot as sort of your starting point. As with the coronagraphs tool, this tool is designed to facilitate direct comparisons between simulated EUV data using PSI's MHD models and real-world EUV imagers. Both this tool and the coronagraphs tool are actively being developed as we work to supply a wider range of available imaging instruments for comparison. So at this time, MHDweb's 2.0's initial release, the only observatory provided is SDO, or Solar Dynamics Observatory, namely the AIA instrument, the Atmospheric Imaging Assembly. The comparison instrument source can be selected from the filter dropdown in the observation widget here. So by clicking this filter dropdown, you'll be presented with the observatory and instrument, as well as the desired wavelength, which can be selected from this nested dropdown. And so as we include more instruments in future iterations of MHDweb 2.0, they will populate this drop-down menu here. Now for a given EUV imager, we fetch their publicly available data through the Helioviewer API, which I covered in some detail in the coronagraphs tutorial video. So the Helioviewer is a resource that allows us to query and download JPEG 2000 images derived from science quality FITS files. This JP2 data is used to generate Sunpy maps and perform the necessary transformations and normalization routines to compare these maps with our model results. Links to these resources can be found in the video description below. And just to reiterate a through line with other comparison tools like time series and spacecraft mapping, the data availability is the principal constraint, dictating which mass runs are viable candidates for analysis. And furthermore, as I mentioned in part 9 of this tutorial for the EUV and X-ray tool, another thing to keep in mind, particularly when selecting your mass run type, is that polytropic models don't possess the same temperature fidelity that is inherent in thermodynamic models. This has to do with the fact that polytropic solutions don't solve for the energy terms in the lower solar corona that are particularly applicable to EUV rendering. Instead, we set the coronal densities and temperatures at fixed boundary conditions. As a result, the solutions possess little variance in these terms, and they yield somewhat smooth EUV plots. If you have selected a polytropic solution through the mass run database, the EUV plot will contain a warning that is notifying you of this, and that warning will show up right in between the simulated and observed plot. Returning to the topic of data availability, SDO's AIA is still actively serving data, so as a result, I can select a recent thermodynamic Carrington run, in this case 2290. The field of view and color map, as you would expect, are defined by the instrument specifications. Radial filtering or vignetting, logarithmic scaling, and color bar scaling can be manipulated through the data widget and view widget. And to get a more detailed description of the different data transformations and how the view widget functions, please just refer to part 9 of this series where we cover the EUV and X-ray tool. Now I want to draw attention to the distinct view selection in the observation widget. So by default, when this is toggled off, the data transformations that are applied from the data widget and the color bar scaling that is applied in the view widget will apply to both plots equally. However, when the distinct view functionality is toggled on, these data transformations and color bar scalings will apply to the observed plot, while the parameters in the data and view widgets will apply to the simulated plot. While we've done our best to apply consistent scaling to both plots as default options, namely to yield scientifically accurate and meaningful comparisons between the simulated and observed data, there can still be disparities between the dynamic ranges of these two data sets. So keeping that in mind, the distinct view option is particularly useful when it's necessary to fine-tune the color bar scaling to yield plots that are not over or undersaturated. For AIA JP2 images that are fetched through Helioviewer, generally speaking, they have a narrower dynamic range than the simulated EUV plots that we have. So as a result, by default, we toggle on distinct view, and we use the minimum and maximum value that are inherent in the data. Now, if I was to toggle the distinct view off, you will see quite clearly the disparities in dynamic ranges between the simulated plot and observed plot. This plot looks quite a bit more washed out. Also, as I mentioned in part 8 of this tutorial series for the coronagraphs tool, we also supply a quality checker within the observation widget. Part of the metadata that is provided by the Helioviewer API is a flag which indicates the quality of the image that is being fetched. So to ensure that this condition is met, whether or not you want to check for the image quality, you can simply toggle this on here. Now, if at the queried time of interest, the plot that is returned doesn't satisfy this quality check, what we do on the back end is search within a 24-hour window of that time of interest for an image that satisfies that quality check flag and returns the closest of these timestamps. Another thing to note is that when querying Helioviewer at a specific time of interest, it will return a plot that is the closest timestamp to that queried time. So keeping that in mind, the time of interest here might deviate slightly from the time of interest that you will see on the plot itself. So for example, if I inspect 2024 at 10:29, we'll give it a second to query that API, do the transformations, and return the plot. And we can see here that the datetime that is returned from the Helioviewer API, while it's very close to our time of interest, is just a little bit off. It's 9 seconds ahead. And while practically speaking, this is a pretty negligible difference, this is worth bearing in mind when you are examining times of interest that lie at the start or end of a mass run. What can happen is by querying the, for example, absolute start of the mass run, the nearest available image will be just slightly before the mass run, and you'll get a validation error that says that the Helioviewer API can't find an image within this time span. As with the EUV and X-ray tool, the resultant plot can be downloaded as an image here, or as a FITS file by clicking the download data icon right next to it. So we provide access to the simulated EUV image data. However, to directly download the FITS or JP2000 file for the observed instrument, visit the Helioviewer API documentation, which I'll provide as a link in the video description below. With that being said, that concludes this overview of the EUV comparison tool on Predictive Science's MHDweb 2.0. The next video in this series will go on to explore the data access tool. If you have any questions, comments, or concerns, please leave a comment below, and thanks for watching.